Hello AP Statistics students. In this video we are going to take a look at R squared, the coefficient of determination. So our objective here is we will interpret how much of the variability in a response variable can be accounted for by the variability in the explanatory variable. This is called the coefficient of determination, or just R squared sometimes. All right, so what does this do? This answers our question: how good is our least squares regression model? All right, how good is this model at predicting? So there's two ways to answer this question. One, you look at the standard deviation of the residuals. That's what we did last time. All right, that tells you on average how far away are the actual data points from the regression line. The second way is to look at this coefficient of determination, or R squared. Now, the concepts behind this are a little complicated. The calculation is even more complicated, but the actual interpretation isn't that bad. So that's where I want to start, is the interpretation of R squared, the sentence that you have to be able to write. Then we're going to take a deeper look into the background, okay? So back to our great experiment here with grabbing starbursts, all right? So hopefully you remember this one. Mr. Tyson's class recorded data for how many starbursts they could grab. They got this scatter plot. They got this regression line. And we need to interpret how good that regression line is. Now, we did the first one last time, interpret the value of S. All right, we did that last time. S is the standard deviation of the residuals. And so hopefully you remember this sentence here. We wrote this last time. The actual number of starbursts a person can grab typically varies by 4.03 starbursts away from the number predicted by the least squares regression model, where x equals handspan. All right, so remember the S value, which in this case was 4.03. That is the standard deviation of the residuals. Now we're going to take a look at R squared. So in this case, R squared is 0.697. So that is a percent. That is 69.7%. And what does that percent mean? So this means if R squared is equal to 69.7%, all right, what that means is 69.7% of the variability in the Y variable. So I'm going to put the context for the Y variable. The number of starbursts a student in Mr. Tyson's class can grab. All right, so that whole thing was just the context. So 69.7% of the variability in the response variable can be accounted for by the least squares regression line, where x equals handspan. Hopefully you can see how that is a similar sentence to our previous one for the standard deviation. The second part is definitely the same. But this time we're talking about the variability in the response variable. 69.7% of the variability in that response variable, the Y variable, can be accounted for by our regression line. Okay? That's the sentence you want to be able to use. That is the sentence frame that you want to be able to use. Make sure that you can see that the variability in this whole thing right here, all the way to here, that is just the context for the response variable. Okay, So make sure you add in that context. All right, yeah, let's talk about this whole sentence. What is all this talk about? The variability in response variable is accounted for by the least squares regression model where x equals the explanatory variable. What does this mean? All right, so let's go in the background of what r squared actually means. So here's a simplified version. Suppose Mr. Bolt is selling pizza as a side hustle to bankroll his wood shop. His pizzas start at $10 and each topping is an extra $2. All right, so whoa. No. We don't get to eat that kind of pizza. That's bad for you. There you go. We're eating nice, healthy pizza here. You got to get your veggies. All right, so we've got here, I made a quick scatter plot. This is a nice, perfectly associated association where our price starts at $10 and just goes up by $2 per topping. So I think the key to understanding r squared is seeing the difference between these two questions on the right. Is the total price of the pizza accounted for by its toppings alone? All right, is the whole price of the pizza just because of the toppings? And hopefully there you can see the answer is no. All right, the whole price of the pizza does not just come from its toppings. The whole price of the pizza starts at $10 right here, even with 0 toppings. So $10 is sort of our starting point. Then we add the $2 per topping here. So I'm hoping you see that the answer to this question is no. All right. A pizza with no toppings still costs $10. All right, so the total price of the pizza is not completely determined by the toppings. There's other stuff involved. Now compare that with this question. Is all of the change in price accounted for by the change in toppings? Okay, so we started out at $10 and then our price changes by $2 and goes up to $12. Is that completely explained by the toppings? Well, yeah, I hope so. It's it's one topping and one topping costs $2 and so our price went up $2. If we add another topping, our price goes up another $2 because the topping costs $2. And so this change, okay, is accounted for by toppings alone. All right, yes, each topping adds $2 exactly to the price. So in this case, we can now say that 100% of the variability in the cost of a pizza from Mr. Bolt's side hustle, all right, 100% of the variability in that cost comes from toppings. Okay, that's the only way the price is being variable. All of that change comes from toppings alone. Now, that works here because this is a perfect association. All right, this line is perfectly linear. So in this case, r squared would be exactly 1. Okay, and of course, when you turn that into a percent, that becomes 100%. Now, most associations are not perfect. So that 100% goes down. And so not all of the variability in the y can be accounted for by our regression line or the variability in the x, okay? So in a non-perfect association, not all 100% of the change in the y values can be explained by the change in the x values. But a lot of it can. How much can be explained? That is what r squared is, and that is what r squared means. All right, let's do one more example of this. We're going to go back to our Ford F-150 example, okay? So if you remember here, the price of a Ford F-150 being sold as used is being predicted by how many miles are on the truck, okay? So I plugged all these numbers into my calculator. I did a linear regression, and my calculator gave me this number right here. R squared is 0.66. All right, and this is what you're going to be doing. You're either going to get a computer printout or a calculator readout of what r squared is. So take a second. Can you write the sentence for r squared? Pause the video. See if you can use the sentence frame from the beginning of the video to write what r squared means and tells us. All right, my turn here. So r squared is about 66%. So I'm going to say about 66% of the variability in the price of a used Ford F-150 can be accounted for by our least squares regression model, where x equals miles driven. All right, so 66% of the price, all right, 66% of the variability in the price of a Ford F-150 is accounted for by our regression line here. Well, that means 34% must be coming from other sources, all right? So this kind of implies 34% of the variability in price comes from other factors. And I'm hoping that kind of makes sense. When you go to buy a used car or truck, yeah, the number of miles on that vehicle matters a lot. But it's not the only thing that matters. You might have a low mileage car that was driven by someone who was smoking. That will drive the price down. Maybe there's gum on the seat. Or maybe it has a lot of miles, but the car was immaculately taken care of and it is just perfect on the inside. Well, you might be willing to pay more even though it has a lot of miles. So a lot of the variability in price, 66%, is accounted for by how many miles have been driven. But 34% are coming from other factors, other things that we just don't know from our data set. All right, that is r squared. Now, I'm going to talk about how to calculate r squared. You don't necessarily need to see this. If you want to peace out right now, no hard feelings, go start your homework. If you want to see the calculation for r squared, stick around. Let's do some algebra. All right, I think this is kind of cool, but if you don't want to listen, have a good one. No hard feelings. All right. All right, if you're still here, let's do this. Back to our starburst example. So remember, the explanatory variable is handspan, and the response variable is the number of starbursts they were able to pick up with one hand. So the first thing we do to calculate r squared is we find the sum of the square residuals. So remember, a residual here is this distance right here, but then we square it, and we do that for all of them. We find the residual, and then we square it. And we add up all of those squares. So this is the sum of the squared residuals. So remember, that will be the y value minus the predicted y value. And so you do that for all the data points. Now that's really tedious, so I used Excel to do it for me. So I've got my data right here. I used the data and the regression line to calculate all the residuals. Then I squared the residuals, and I added them all up. And I got 346, let's go 0.5, we'll round that up. So 346.5. Then you do an interesting thing. You do another sum of the square residuals, but you use a different regression line, all right? You use simply the average value as your regression line. So if I did that, the average value here is 28.2. So the average number of starbursts a kid could grab was 24.2. Okay, because that's a decent estimate. If you say, hey, how many starbursts could a kid grab in Mr. Tyson's class? Well, they averaged 24.2. And so you could just say 24.2 instead of using the regression line to find a prediction. And so that would be somewhere in here. I don't exactly know where because I don't have my scale. But you could use this as a prediction for everybody, just a catch-all. And so what we do is we find the residuals not to the regression line, but to the average. Now, obviously, this is not as good as a predictor as the regression line, right? The sum of these residuals is going to be much, much bigger. All of these squares are going to be much, much bigger, pretty much all the squares, than the regression line, okay? Just reporting the average is not nearly as good a predictor as our regression line, but we can still use it. And so we do that, and so here we do the sum of the squared residuals, but our residual, instead of using the predicted value, it's the average, y bar. Now this number is going to be much, much bigger. So that's 1,187, roughly. 1,187. And then what we do here is we think, all right, how much better is our regression line than just our average? Okay? How much better is the regression line than the average? And we do that by a percentage. So what we do is we take the 1187 minus the 346.5, and then we turn it into a percent by dividing by 1,187, the total. So what percent decrease did we have? All right, we went from 1,187 and we went down to 346. How big of a decrease was that in variability? How much better is our regression line than our average value? And so you type this into the calculator, which I don't have up right now. So 1187 minus 346.5 divided by 1187, and we get 0.708. which, as you can see, is the r squared value. Now, this kind of blows my mind, actually, that this works, because r squared is just the square of r. And so if I write this whole thing as one big equation, so what we just did is we took the sum of y minus y bar squared. Then we subtracted the other square residuals from the predicted value y hat squared. And then we divided by the total, the big one, which is this one, y minus y bar squared. That is r squared. Now, why is that equal to the square of this number, which we did last time? That's a completely different calculation. The correlation was the sum of 1 over n minus 1. Oops, that was on the outside usually, wasn't it? 1 over n minus 1 of the sum of the x z-scores times the y z-scores. Oops, that should have been a y as well. Over the standard deviation of y. So this is our calculation for r squared. This is our calculation for r. And so if we square this whole thing, they both become r squared. Why are those two equations the same? I will definitely give you some extra credit if you can ever tell me how and why those two equations are somehow the same. We calculate r completely differently than we calculate r squared, but one number is just the square of the other. If we do r, which is 0.84, 0.8415, and we square that, we get 0.708. I have no idea algebraically why those two very different calculations are so closely related. I think it's really cool. All right, if you made it this far, congratulations. I hope the sentence for r squared makes sense. You definitely don't need to know all of that, but you do need to know the two ways that we can talk about how good a regression model is. One of them is to look at the standard deviation of residuals, and the other is to look at the coefficient of determination, r squared.